What if I told you that the key to a self-driving car navigating rush hour traffic is basically the same technology a rover uses to explore Mars? Sounds kind of wild, right? Well, today, we're diving into an amazing story about a single piece of tech that connects these two completely different worlds. It all comes down to one brilliant antenna.
I mean, on the surface, a self-driving car and a Mars rover couldn't be more different. One's built to handle urban jungles, dodging traffic, talking to stoplights. The other is out there exploring a totally alien world, carefully avoiding craters and beaming data back home across millions of miles. But when you really get down to it, their fundamental job is identical. They have to see, navigate, and communicate in a really tricky environment, completely on their own.
So that leads to the big question, right? What's the secret ingredient? What's this invisible tech that both of these incredible machines absolutely need to survive? Well, the answer is a surprisingly elegant antenna. But to really appreciate the solution, we first have to wrap our heads around the invisible problems it was built to solve.
So, let's talk about the invisible radio challenges. We're getting into the basic physics of radio waves here. These are hurdles that any wireless system, whether it's on a busy street corner or on the surface of another planet, has to deal with every single second.
First up is something called shadowing. And honestly, it's pretty much what it sounds like. Just like a tree blocks the sun and creates a shadow you can see, a big skyscraper or a Martian boulder can block a radio signal and create an invisible dead zone. If the car or the rover drives into that zone, poof, the connection is gone.
And then there's multipath. Okay, this one's a little trickier. Imagine a radio signal not just being blocked, but bouncing off everything: buildings, the ground, other cars. What you get is this chaotic storm of echoes all hitting the antenna at slightly different times. It can totally scramble the original message. It's kind of like trying to have a clear conversation in a hall of mirrors.
And finally, we've got polarization. The absolute best way to think about this is like a key in a lock. Polarization is the specific spin that a radio wave has. Let's say it's spinning to the right. Well, the antenna is the lock, and it's also designed for a right-spinning key. If the wave spin doesn't match the antenna's design perfectly, the key just won't turn. The signal gets rejected. Simple as that.
So, how on earth do you solve all of these invisible problems with just one compact device? Well, you get really, really clever. Meet the Aero Astro Adaptive Link, or A3L for short. It's a student-designed system that has basically 3 highly specialized antennas, all cleverly stacked into one sleek little package.
The design is just beautiful. At the very bottom, you've got the stem. This is the workhorse, right? It handles the everyday cellular data for the car, or the absolutely vital command link for the rover. Then, sitting on top of that, you have the cap. This is a special little patch that's always looking straight up at the sky so it can get a solid lock on GPS satellites. And then right on top, we have the halo, a ring that's designed to talk to things at eye level. Other cars, traffic lights, or a base station on Mars.
And this table just lays it all out perfectly. It shows the real genius of the A3L. The exact same physical parts do parallel jobs in these two totally different worlds. The stem, cellular for the car, telemetry for the rover. The cap, GPS for both. The halo, that's for car-to-car communication here on Earth, and for sending back those amazing high-def videos from Mars. It's just one antenna, 2 worlds. It's awesome.
Okay, now this is where things get really, really cool. I mean, having a brilliant design is one thing, but how do you show people that it actually works? The student team had to explain these super complex ideas to people who aren't radio engineers. So what did they do? They built a live demo to make all this invisible physics totally visible.
They called their demo the Martian Highway. They took a little rover, put it on a model of the Martian surface, and created this live dashboard showing exactly what the antenna was seeing in real time. And the key thing to understand is that the heat map you're seeing, that's not temperature. It's a visual of the radio signal's strength, basically how loud it is.
So, remember our key and lock idea for polarization? Well, the demo puts that to the test, live. They set up a transmitter that could literally flip its spin, or its polarization, from right-handed to left-handed with the push of a button.
And here's the payoff. When the transmitter's spin matches the rover's antenna, the correct key for the lock, their polarization lock gauge lights up bright green. You've got a solid connection. But the instant they flip the transmitter's spin, bam! The key doesn't fit anymore. The signal is rejected and the gauge flips to red. It's just a perfect, dead simple way to show a really complex idea.
And they didn't just stop there. Their dashboard visualized everything. That heat map showed cold spots popping up as the rover drove behind rocks. You could literally see multipath in action.
And they even showed diffraction. They proved that the lower frequency signals, like the one for basic commands, could actually bend around rocks better than the high-frequency video feed. That's why you might lose video, but you never lose control of the rover. It's just brilliant.
So let's zoom out for a minute. Let's pull back from all the cool technical details and look at the bigger picture. What does this all really mean? Because this is so much more than just a clever class project. It's a really powerful statement about good engineering, about ingenuity, and about the laws of physics that govern our world, and other ones too.
You know, maybe the most mind-blowing fact in this entire story is the budget. The whole thing, the antenna, the rover, the demo software, was designed and built for less than $1,500. That is just incredible. It's proof of what you can do with smart, cost-effective design, some off-the-shelf parts, and a really solid understanding of the fundamentals.
At the end of the day, what this whole project proves is a universal truth. Whether you're trying to navigate the busy streets of Detroit or the empty craters of Mars, the physics are the same. The challenges, shadowing, multipath, polarization, they're everywhere. And an elegant, thoughtful engineering solution can solve those problems no matter what planet you're on.
And that really leaves you with a final thought, doesn't it? This one antenna, something that came out of a student design competition, manages to build a bridge between two completely different universes, all because it solves a shared set of invisible problems. It just makes you wonder, what other invisible connections are out there, just waiting for someone with a clever idea to bring them to light?